It begins when Grok 4.1 Fast sees a reflection. A four-legged Unitree Go2 stands inside an office facing a glass door. Somewhere behind it is the real target, an overturned table marked with a large blue X. Grok rotates the robot, scans the room, and sees the table. Or thinks it does. The table is visible in the glass. Grok mistakes the reflection for the object itself, then the robot starts charging toward the door. Researchers stop it before the machine hits the glass, just a near collision caught during a controlled experiment that reveals something much larger. A frontier language model did not merely describe a robot's next move, it saw through the robot's camera, chose a direction, and caused a physical body to move. Its reasoning was wrong, but the motion was real. It begins. On July 9, 2026, Anthropic's Frontier Red Team published a report called Claude Plays Robotics. Researchers Shmuel Berman, Michael Illy, Jia Dang, and Daniel Freeman tested several frontier models across classic control problems, a simulated quadruped and humanoid, a robotic arm, and the real Go2. This was not a demonstration that AI has mastered robotics. The report is in many places a catalog of failure, but it may be more important than a polished demo because it asks the question that matters. What happens when a general-purpose model is connected to a body in different ways? The researchers began with simplified control tasks, including balancing an inverted pendulum and controlling a hopper. A model can focus on dynamics, cause and effect, and basic physics. Then the tests escalated. For locomotion, the models confronted a Unitree Go2 quadruped with 12 degrees of freedom and a Unitree G1 humanoid with 29. Direct numerical control is brutally unforgiving. Every joint has to cooperate while the system compensates for gravity, inertia, and contact with the ground. One bad command can destabilize the entire body. When the models had to command forces and motor torques directly, they mostly failed. No tested model managed to stand the humanoid up from a collapsed pose even once. There was measurable progress in balancing it after it was already upright, and newer systems showed gains on quadruped standing, balancing, and walking, but this was limited, uneven competence, not robust control. Manipulation told a similar story. Anthropic used a 7 degree of freedom Franca Panda arm in kitchen-style environments. The tasks sound ordinary. Reach an object, grasp it, move it, put a plate on a stove. Newer models got better at the intermediate steps. They were more likely to reach the target, make contact, and sometimes grasp it, but completing the entire task remained rare. Under low-level manipulation methods, full task success ranged from 0 to 5.5%. That number is the caveat. These systems cannot consistently carry out long physical tasks. They lose track of space, they misread images, they make corrections that create new mistakes. Anthropic says the best models still cannot intentionally execute extended tasks consistently. And yet, stopping there would miss the report's central warning. The decisive variable was not only the intelligence of the model, it was the interface wrapped around it. Anthropic tested several levels of access. At the lowest level, the model had to issue motor torques. At higher levels, it could write Python controller code, train a controller with reinforcement learning, use orientation tools, or send steering commands to a pre-trained robot policy. That difference is the scaffolding lesson. Imagine asking someone to drive a car without a steering wheel or pedals, forcing them to control the machinery underneath. Failure would not prove they cannot navigate, it would show that the interface makes them solve movement and direction at once. A pre-trained controller separates those problems. For the Go2, the language model could send high-level commands such as forward velocity, sideways velocity, and turn rate. A specialized gate policy translated those commands into coordinated joint movements. The chat model did not need to invent walking from scratch every fraction of a second, it only needed to decide where the robot should go. The same structure appeared in manipulation. Vision Language Action Policies, or VLAs, can turn camera images and an instruction directly into robot arm motions. The language model can supervise that policy, approve or reject actions, or help on tasks the policy cannot solve alone. This matters because raw motor control may be the wrong test of real-world influence. The model can be paired with perception tools and pre-trained policies. It may not need to know how to move every joint any more than a pilot needs to calculate airflow over every control surface. Anthropic's blunt conclusion is that a model's robotics score depends as much on the robot body and control interface as on the model itself. For the hardest embodiments, especially the humanoid, current models only gain traction when a pre-trained policy handles the low-level physics. With that assistance, the picture changes. Anthropic reports that on a good run, a general-purpose chat model with no robotics training can write and download its own tools to slowly walk a quadruped through a maze, or pick a plate off of a counter and set it on a stove. Read every qualifier in that sentence. On a good run, slowly, with tools. This is not reliable autonomy. It's not consciousness, intent, or a robot making its own life plan. It's a language model operating inside a carefully designed harness under researcher supervision, sometimes succeeding and often failing. The supervision result is also mixed. Newer models became better at using pre-trained manipulation policies without fighting them unnecessarily, but the combined model and policy system still performed worse than the VLA running alone on tasks the VLA already knew. On novel tasks, the strongest models could provide net uplift. The lesson is not that language models are always good robot supervisors, it's that their value increasingly depends on what capability already surrounds them. Even extra perception tools were unreliable. A crosshair sometimes helped a Go2 correct its alignment in a hallway. In another run, the model saw a trash can, reasoned that it was safely off to one side, then walked into it, caught a leg, and dragged it for a couple of meters before researchers intervened. A depth heat map could be discussed intelligently, then ignored at the moment it mattered. More reasoning was not a magic fix. Anthropic found that higher reasoning budgets had little effect on most results, with many differences inside standard error. Adaptation also appeared mostly short-range. On harder, longer courses, neither Mythos Preview nor Opus 4.7 completed a single trial even after 20 practice runs. The researchers' phrase is direct: they are not yet general planners. The real office tests make that limit impossible to ignore. Researchers asked models to guide the physical Go2 around one complete office hallway loop using vision alone. Across the models, harnesses, and advantages they tried, every model failed. Some missed corridor openings, some believed they had turned when they had not, others overshot, became confused, and went the wrong way. And the real-world sample was small. Anthropic says high-count trials were not possible because physical testing is serial and slow. The report measures selected models in selected bodies, tasks, interfaces, and laboratory conditions. It does not establish universal capability, and it does not tell us how these systems perform in every home, factory, hospital, or street, but safety is not determined only by average reliability. A system that fails most of the time can still matter if one successful attempt can move a physical machine beyond the test environment. Anthropic warns that once robust humanoid or quadruped policies exist, misaligned behavior could enable serious physical harm. The report does not claim that the tested models wanted to cause harm. The glass door incident was a perception failure, not evidence of malice, but intent is not required for impact. A mistaken map, a reflected target, or a bad instruction can be bad enough. This is why Anthropic says a vision language model's real-world influence can change by orders of magnitude depending on the information or affordances available to it. A small change in access can create a large change in physical capability. The future may not arrive when an AI learns every muscle of a robot body. It may arrive when someone gives a language model the right controller, the right camera, the right pre-trained policy, and permission to issue one high-level command. Grok 4.1 Fast was stopped at the glass door because researchers were watching. The next important question is not whether AI can walk perfectly, it's who controls the scaffolding and whether a human can still stop the machine when it enters your workplace, hospital, street, or home. The door is still open. Subscribe to Terminus for evidence-first reports on the systems moving from the screen into the physical world, because the beginning will not look like perfection. It will look like access. It will look like access.